We are Group 1 and our team name is Agama. It stands for Alexa, Gerardo, Alexandra, Mariana, and Aaron. For our final project for this class, we had to come together and use the engineering design process to create a bridge that fit the criteria our professor gave us. For the bridge project, we looked at the requirements and guidelines to see what we needed to include in our design. Once we knew what we needed, we started doing our research to find the best components to have in our bridge. We had to design it so that it fit and didn't go over the given dimensions when we 3D printed it. We also had to make sure that once it was 3D printed, it could sustain at least the 15-pound weight we will add to it. We started looking for the best support base for the bridge that could hold the weight, which we decided on an arc base. Our final design was a Warren truss bridge with an arc base for better, stronger support. Once we 3D printed it, we are going to test it to see if we have the best bridge and can use the engineering process to solve real problems.
We chose a Warren type of truss because it's composed of equilateral triangles. When these triangles are arranged together, they form a more complex, lightweight, efficient, and well-structured truss. Equilateral triangles help to spread more force across the bridge, making the bridge a lot stronger, minimizing the forces to only compression and tension. Since we chose a Warren truss, we added a flat roof to the sketch. This will come in handy to maintain the structure's stability without collapsing when the 15 pounds are added. Also, by having this truss, it makes it easier to place power lines through the top of the roof.
For the power lines, since we used the Warren truss design for our bridge, we arranged the cables to go on top of each side instead of following the triangle pattern on the sides. We chose this option over all the others because it is more convenient and economic for the cables to be installed this way. We also learned that the power flows more efficiently when the power lines are straight instead of bent or curved every few centimeters.
The next step to building the bridge is figuring out where on the bridge would be most convenient and efficient in placing structures for water. We came across that having the water tubes embedded into the bridge would ease the transportation of water. Therefore, we decided to make two cylindrical openings through the bridge and in between the Warren truss beam and the arc deck, which would represent where the structures of water would be placed.
Our deck is based on the design of the arc base. Arcs can support heavier weight than rectangular columns because the arc spreads the force of the weight on top of it outward. The arc will distribute the whole weight on each end of the bridge instead of pushing it straight down like a suspension column. The arc gets its strength from its shape, which will stay in place for a very long time if the blocks don't move. That is the reason why arc bridges last for a long period of time. It was measured with a wide deck, which will support the whole weight above, including the Warren truss.